Welcome to a very exciting edition of Rebellion's educational series. We have a living legend with us, a professor who I have looked up to for over 20 years. Professor Yann LeCun of NYU is also head of AI for Facebook. His work with computer vision has redefined the field. He's considered a godfather of CNNs, a godfather of deep learning, a godfather of AI, really. And to have him with us is such a true honor. For someone like me who spent his whole life in machine learning and AI, this is truly a dream come true to have you on the show, Professor LeCun. Thank you so much.
It's very nice to meet you. It's very nice to be on your show as well.
So let's start with deep reinforcement learning. It was only brought to me recently by a student, and it seems to be a very exciting fusion of deep learning and reinforcement learning. Do you have an opinion on it? If so, obviously we'd love to hear.
I actually have pretty strong unorthodox opinions on this, on reinforcement learning in general. So, in the context of machine learning and AI, machine learning has kind of taken over AI to some extent these days. And there are sort of three types of learning that people use, three paradigms. The most common one that everybody uses is supervised learning. And there is the less common one, reinforcement learning, which is used mostly for games. There is a bunch of applications, real world applications in which it's used, but it's a very small number. And then there is unsupervised, self-supervised learning, something that's kind of ill-defined, which is perhaps the type of learning that we observe in animals and humans. And the question is, where is the future of AI? So as I said, now almost all of AI is supervised learning. Almost all of machine learning is supervised learning. A little bit of it is reinforcement learning. And a growing number of it is actually based on what's called self-supervised learning, particularly in natural language processing, a little bit in computer vision. So what makes the difference between all of those things is that in supervised learning, you tell the machine what the answer is for every example you show it, right? So you show it an image of a car or a truck or, an elephant or a table, and you tell it this is a truck or an elephant. And if the answer is different from what you want, the one you want, you adjust the parameters so the answer gets closer to the one you want. In reinforcement learning, you don't tell the machine the correct answer. You just tell the machine, the answer you produce was good or was not so good. Okay, so you give it some sort of rating on what, how good the answer or bad the answer was. And what the machine needs to do is figure out in which direction to change itself so that its answer gets closer to the one you want. So this rating is called the reinforcement or the value function actually. Mm-hmm. You don't know this function, and so the machine doesn't know this function. It has to try things to figure out how to improve itself. And then self-supervised, unsupervised learning is more like, learning about the world, learning how the world works without actually directing it towards a particular task. And so reinforcement learning has, excited people a lot over the last 6 years or so, 5-6 years, because of big success in games like, Atari games, video games, chess, Go, things like that. And what you notice there is that those machines require an enormous amount of interactions with the game to be able to learn things. So the best Go players have to, that train themselves, they have to play the equivalent of, tens of millions of games before they play well. And there is a system put together by DeepMind to play StarCraft. And that StarCraft, to play just on one map, has to train itself for the equivalent of 200 years of real-time play, which is way more than any human, of course, on StarCraft. So reinforcement learning is very powerful, but it's unbelievably inefficient in terms of number of trials.
Oh.
And that's because it has to be trained from scratch. The system has to learn absolutely everything from scratch.
So it needs to really operate in a vacuum of sorts. It has to be spoon-fed everything. And so, I guess it makes it limited, but where do you see it kind of moving from finance in games?
You could add for a bit, so I
Sorry,
didn't
what?
hear the question.
Oh, I said beyond finance and games, where do you see reinforcement learning moving?
Well, yeah, I mean, interaction, like situations where you have some sort of ongoing process that you have to learn online, reinforcement learning can be used. But there, there's a lot of those situations where the objective is very clear, and you don't need to, you know, you can use supervised running, right? You want to do time series prediction, for example. Time series prediction is a form of supervised running. And, or you could say self-supervised running, because the data you use to train the machine is of the same nature as the input it observes. And so there, you don't need to use reinforcement learning, because reinforcement learning is the situation where the cost function is not clear. You know, it's not clear what, like how to compute how well you're doing. You have to be told how well you're doing by some external system.
So jumping to deep learning, do you think it's overhyped?
I think it depends on who you talk to. So I think, or who you listen to, right?
Yeah.
So there are certainly a lot of people who are going to overhype deep learning, and those are people who are either looking for money or attention, essentially.
Oh.
Okay. And there are people who are completely realistic about the possibilities of the potential outcomes of deep learning. And those tend to be, you know, the people who are more kind of on the science side of things, on the research side of things. So people on the research and science side of things are well aware of the limitation of the techniques they use, and they don't have a very strong incentive necessarily to oversell what they're doing. Except to their peers, but their peers are trained to detect BS, so you know, it doesn't work very well. But you know, in the context of industry or the media, then it's different, right? Or the public, there is a lot of hype going on there, and it has to be called, because it creates very high expectations for a lot of people who then do not get fulfilled. And when that's happened in the past, in the context of AI, it created you know, a big kind of disappointment and an AI winter, essentially, where people said, like, you know, you promised me the moon and you're not delivering it.
Well, you're a professor at Courant, and I was at the NYU Career Fair last fall, and almost every other quant student came up to me and started talking about Q learning. So do you think, you know, Q learning is overhyped?
Yeah, possibly. I mean, it's very useful in some situations. I think there are a lot of situations where people attempt to use reinforcement learning, and there are situations where reinforcement learning is really not the most efficient thing to do.
Yeah.
So, you know, if you're a quant, you want to take the right action, but you also want to model the market or the set of financial instruments you're manipulating, or you're investing in, or you know, making decisions about. And so one part, the second part here is prediction. And then, given that you have good prediction, given that you have a good model of the system you're trying to control, what action are you going to take? So for the first part, modeling the system, we're not talking about reinforcement learning here. We're talking about essentially supervised or self-supervised learning, time series prediction, essentially. Then for the second part, it depends what quantity you're optimizing. So you want to, you know, maximize return, and it could be that the sequence of actions to do so is not cannot be derived, you know, directly from your predictions. But it could be that they can. Okay, so there are two, you know, classically going back decades, there were sort of two ways to approach this kind of problem. One is reinforcement learning, and the other one is optimal control. Okay, and in many situations, the right thing to do is more akin to optimal control than to reinforcement learning. And it's much more efficient in many ways.
Professor LeCun, just the idea came to me while we were speaking. I know you were at Bell Labs. Was deep learning used at Bell Labs? Or if you can't answer that, that's okay. I don't.
No, of course I can.
Oh, okay.
It wasn't called deep learning at the time. It was called neural nets, or
Okay.
you know, multi-layer neural nets, right? They became we changed the name, you know, in the mid 2000s, basically to kind of reflect the fact that the systems we're using were not only neural nets. They were kind of slightly more general than that. But yes, at Bell Labs, I joined Bell Labs in late 1988. One of the first things I did was you know, develop convolutional nets, and I applied them to character recognition. And AT&T eventually built a bunch of systems based on this technology that were commercialized for reading checks, for
No. Your computer vision
forms.
technology made it possible for banks to read checks. You completely changed the game for finance. So no, that's some of the work that I first read about when I was still a student myself, and when I first came across your work as a researcher. So you'd say deep learning was around in the 80s or as early as the 70s, or
No, but late 80s really was when things started. So I mean, the backpropagation algorithm that is universally used for training neural nets, popped up around 1986, 1987. And that's really what enabled multilayer neural nets. And then convolutional net popped up around 1988. And that's what enabled us to do computer vision essentially, but at the time it was black and white images and stuff like that. Phase detection, but like very few applications were practical because of lack of data and compute power. But character recognition was certainly a big successful thing. Those were deployed commercially by AT&T around 1994, I think the first applications, and continued on until the early 2000s essentially.
are you trying to make Facebook AI more like a Bell Labs in terms of your research, or?
It is very much like Bell Labs in many ways. I mean, when I started Facebook AI research, and when I joined, that was kind of what I was asked to do, and I drew on my experience from Bell Labs and AT&T Labs. I also worked briefly at NEC Labs. I worked at a couple other companies. I had many friends in various industrial research labs. So I knew how research in industry can be successful. So I picked some of the best ideas from Bell Labs, Xerox PARC, IBM, Microsoft Research, etc., and sort of try to create a research organization that is both ambitious in its goals, so can do long-term research where people are not sort of directed top-down. The research done at Facebook AI Research really is bottom-up. The researchers pick their topics, but at the same time, establish channels with the development group so that whatever innovation comes out can have an impact on product. And that's been very successful, actually.
Are you guys working from home still, or are you back at the office?
Yep. It's all remote. Yeah.
Oh, wonderful. So jumping back to general adversarial networks, what's your feeling on that? Is that the architecture of the future?
Generative adversarial networks, yes, GANs. No, yes and no. Okay, I think it opened the eyes of a lot of people, including me, on kind of new ways of building neural nets or learning systems that basically capture the structure of data. All right. And
how do they differ from like a Bayesian neural net?
So they're not Bayesian at all. They're not even probabilistic, actually. I mean, they claim they are, but they're not. So what a GAN does is that it can turn a bunch of random numbers into a structured object, let's say an image, right? So you train a neural net so that when you draw a random set of numbers, say 100 random numbers from, say, a Gaussian distribution or something like that, you run it through this neural net. At the other end comes out an image of a face, for example, or a dog or something like that, right? And by, when you change those random numbers slightly, what you get is a slightly different dog or a slightly different face. And so that's the idea of a generative model. Some of them are probabilistic, some of them are not. GANs are not really probabilistic in many ways. They don't model the density of the, probability density of the output. But they are kind of a really interesting set of methods, and I was really excited about them for a while. I'm less excited about them now. I'm trying to replace them by something more efficient because they have some flaws, which can be a little technical. But so I'm trying to find a somewhat general method to train machines to learn the structure of data without being trained to do a particular task. And
that's very cool.
Our particular way of doing this.
That's very cool. Well, speaking of training, do you think that would training a single model on multiple problems at once is, I guess, one neural network that can do both face and speech recognition, would that be more efficient, do you think, in the future?
Sorry about that. I had to disappear for just a couple of seconds to
Of course.
change the lighting. Yeah. Okay. So there is this big question as to how do you make learning machines more general than they are, right? You train a system to do image recognition on a particular data set, and you show images that are, slightly different from a slightly different context or whatever, and those systems are somewhat brittle. Sometimes they focus on biases in the data that really are irrelevant. So for example, you train a system on the standard data set that everybody uses called ImageNet. One of the categories is a cow, and all the cow pictures are cows in a field. And now you show the system a picture of a cow on the beach, and the system doesn't say it's a cow because every single cow it's ever seen has been on a green background. And so it's using the context to make the recognition. And in this case, the context is different, right? So to some extent, it's not completely figured out the concept of cow. So that's the question. How do you make those systems less specialized and less brittle? So what's called multitask learning, which is what you're describing, you train the system not just on a single task, but on lots of different tasks, or on some task that is so general. It may not be the task you're interested in at the end, but it's much more general. So let me give you an example. A few years ago, the best computer vision system that Facebook was using was trained, was a big convolutional net. It was trained to predict the hashtags that people type on Instagram when they upload a photo. And so the engineers, selected something like 17,000 different hashtags and then trained some giant neural net to predict which of those 17,000 hashtags would be present in any particular picture. It's not a particularly interesting task, but that neural net was very well trained to be able to recognize just about anything afterwards. So what you do afterwards is you chop off the last layer and you stick a new last layer, which you train for the tasks you want. And because the bulk of the neural net has learned how to, recognize images, now you don't need many samples to train it to recognize a cow or, a truck or a table. So that's this idea of weakly supervised learning or transfer learning, right? So you train on a very general task and then you specialize the system on a new task. So you can do multitask, you can do transfer, but ultimately what people are working on now in computer vision, and they've been working on this for a while in natural language processing, is self-supervised learning. So you train the system not to recognize anything, but to represent the data in some way, in some good way. And then you use this pre-trained system as input to the system that does the task that you want, that recognizes objects, or in the case of text, does translation or whatever. That has been astonishingly successful in natural language processing. And so far, not so much in vision, but it's making very fast progress.
Oh, very cool. Well, speaking of progress, well, we're coming to the end of our show. I guess, what are you most excited about in the world of AI right now?
Well, this whole idea of self-supervised learning really, the big question we need to solve is that you observe someone like a young child, learning to manipulate objects, or a young child learning new concepts, right? You show a young child a few pictures of an elephant. It doesn't need to be a photo, it can be a drawing. And this young child will know what an elephant is, right? Regardless of pose and everything. You are 17 or 16, you learn to drive a car, in about 20 hours of training, you can learn to drive a car. Maybe not perfectly, but you've done a pretty good job. And almost no one has told you, here is how you drive a car. You basically kind of learn more or less by yourself. Now, if you were to take, today's machine learning system, supervised or reinforcement learning, to manipulate, to recognize objects, or to drive a car, it would take millions of trials, millions or billions of examples, and millions of hours of practice, causing many accidents in the case of self-driving car. This is one of the main obstacles actually to completely autonomous driving. And so,
then I guess you'd agree that Elon Musk's Tesla's lead is quite severe then.
I mean, he's not very much ahead. I mean, Tesla is not
Oh,
very
really?
much ahead of everyone else. No, no, no.
You think it's
Not
2
at all.
years ahead, a year ahead? What would you put it at a number?
Nobody is, much ahead by more than a few months than anybody
Oh,
else.
really? Oh,
Yeah.
very interesting. I'm so glad I asked you that.
I mean, in terms of concept, algorithms, etc. Some people invest in hardware a long time, and if the hardware turns out to be really important, it's very hard for other companies to catch up, but eventually they do. But like in AI research, development is a different thing, but in AI research, nobody is ahead of anybody by more than a few
Professor
months.
LeCun, so many of the biggest fund managers I know from Fidelity and whatnot own Tesla stock because they believe that they'll have 5 to 10 years of a monopoly on driverless technology. And that's what they think the value is.
That's probably wrong.
Oh, really?
Yeah.
Wow. That's
But
unbelievable.
where they may have 5 or 10 years in advance is battery technology, because they have the big factories that nobody else is building, and it takes many years to build them. But AI, no, I doubt it. I think a lot of other companies have kind of similar technology. They may not have enough, the same amount of data. They may not have the same kind of specialized hardware, but they can buy it from NVIDIA and ARM now. So I don't think so.
Your battery storage sentiments are shared by many of the robotics CEOs who come on our show. They've said that energy storage is going to be what allows robotics to move forward. And so that's something we have to move
Well,
forward.
there's many issues in robotics. I think one of them is this issue of self-supervised learning I was telling you about, right? So self-driving cars are, some sort of robot, but what we'd like is household robots. We'd like virtual robots that are, virtual assistants you can talk to, can answer any question you want, that can assist you in your daily lives. And for this, we need to make the next big leap in AI. In my opinion, that will come from allowing, finding ways to get machines to learn as efficiently as humans and animals. As I was saying, it takes too many samples, too many trials for current paradigms of machine learning to learn what humans and animals learn in a few hours. And so what is it that we're missing? We're missing a big piece. In my opinion, it's called self-supervised learning, but we'll see.
Well, this was an amazing conversation, Professor. You are absolutely a fantastic wealth of knowledge. I couldn't be more thankful. And stay safe during these crazy times.
And thank you, you too, and you're most welcome. It was fun.